This is a video for OCR Pure Core Mathematics, Calculus 1 Improper Integrals, 1.4 Integrals that cross a value where the function is undefined. Let's have a look at this function. It's the function 1 over x minus 1 all squared, and I'm integrating that between 0 and 3. The graph shows me that there's an issue potentially here at x equals 1. And looking at the algebra, when x equals 1, the bottom line becomes 0, and I've got a potential problem. The question is, what's the area under the curve? Is it defined? Does it tend to a limit? Or is it infinite? To do that, we're going to have to look at this integral in a slightly different way. Here's my integral, and I've identified that 1 is the potential problem point. What I'm going to do then is I'm going to integrate between 0 and a, and I'm going to allow a to tend to 1, my problem value. And then I'm going to have a second part to this, which is also going to be an integral, but between a and 3. In other words, the rest of it. And again, looking at what happens as a tends to 1. Well, we'll just fill in the bits for that. So this is x minus 1 all squared dx, and this is 1 over x minus 1 all squared dx. Well, the integral of 1 over x minus 1 all squared is equal to minus 1 over x minus 1. And for the first part, it's going to be evaluated between 0 and a. And in the second part, I get the same result, minus 1 over x minus 1, evaluated between a and 3. And again, what happens as a tends to 1? These two parts together cover the entire range that we're trying to integrate. Okay, let's plug in the values then. So I'm going to get minus 1 over a minus 1 from the upper limit. And just need to be a bit careful with the second part of this. I'm going to get minus 1 over minus 1 for the lower limit. And again, look at what happens as a tends to 1. For the second part, I'm going to get minus 1 over 2, and then I'm going to get minus 1 over a minus 1. And again, look at what happens as a tends to 1. Well, what does happen as a tends to 1? As a tends to 1, 1 over a minus 1 tends to infinity. And that means that this bit here and this bit over here are going to tend to infinity. And so the whole thing is undefined. And this integral is in fact divergent. There's that working tidied up for you. And you'll see here we've split this integral into two parts, up to a, and then from a up to 3. And in both cases we're allowing a to tend to 1. Working that on through, we end up with the fact that 1 over a minus 1 does not converge as a tends to 1. And so the integral is undefined. Here's a second example. This is x minus 1 to the minus 2/3, and we're integrating it between 0 and 4. The minus sign in the power suggests I've got a reciprocal of some description, and so I might be concerned when x equals 1. And indeed, the graph shows that there is an asymptote at x equals 1. And just as before, we're interested in this area here. So, same technique as before. We're going to split it at the perceived problem value, so 0 to a, x minus 1 to the minus 2/3 dx, and from a up to 4 of x minus 1 to the minus 2/3 dx. And in both cases, what happens as a tends to 1? Okay, so when I integrate x minus 1 to the minus 2/3, I'm going to get x minus 1 to the 1/3 multiplied by 3. And that is between 0 and a. So the second part is going to be 3 lots of x minus 1 to the 1/3, and that's between a and 4. And in both cases, again, what happens as a tends to 1? We'll plug those limits in. From the upper limit here, we're going to get 3 lots of a minus 1 to the 3rd minus 3 lots of minus 1 to the 3rd. What happens as a tends to 1? Plus, from here I'm going to get 3 lots of 3 to the 3rd minus 3 lots of a minus 1 to the 3rd. And again, allow a to tend to 1. Okay, so what happens as a tends to 1? A minus 1 to the 3rd tends to 0. And so this part and this part of our result are going to disappear. Okay, so that's going to give me minus 3 lots of minus 1 to the 3rd plus 3 lots of 3 to the 3rd. Now minus 1 to the 3rd is just minus 1, so that's going to give me 3 plus 3 lots of 3 to the 3rd. There's it all tidied up again, so here's your split in the integral. That's it at the problem value. Work it on down, and then this part and this part vanish as a tends to 1, and so the integral converges to our final value, 3 plus 3 lots of 3 to the 3rd. So this integral can be evaluated after splitting at the problem value. So the technique is split at the problem value, so up to a and from a on up, and then allow that variable to tend to your problem value and see what happens once you've completed the integral. That was the final video in the sequence Calculus 1 Improper Integrals.